Benoît B. Mandelbrot, a Polish-born mathematician, emerged as a scientific revolutionary in the 20th century. He wasn't just an ordinary mathematician, he was a visionary who changed how we see geometry and the natural world. Mandelbrot brought a fresh and innovative approach, challenging traditional rules and ideas. He challenged the rules of traditional geometry with his groundbreaking work on fractals. Before his work, geometry mainly focused on simple shapes like lines, circles, and triangles. However, Mandelbrot realized that these shapes couldn't fully describe the complexity and variety of natural shapes we see around us. His journey began with a simple question: how long is the coastline of Britain? This question, although seemingly simple, has no easy answer. The length of the coastline changes depending on how detailed the measurement is. This led Mandelbrot to an important discovery: natural shapes can't be measured using traditional geometric methods. This seemingly simple question led him to the realization that traditional geometric shapes like lines and circles are not enough to describe the complexity of natural shapes. Instead, he realized that natural shapes often have a fragmented structure, repeating at different scales. This is a key characteristic of fractals, and it opened up a whole new field of study. Mandelbrot's fascination with irregular shapes and patterns led him to coin the term fractal in 1975. Derived from the Latin word fractus, meaning broken or fragmented. This term not only described the shapes he studied, but also reflected his approach to mathematics and science. He opened a new door, allowing us to see and better understand the complexity of the natural world. This marked the birth of fractal geometry, a revolutionary field that provides a new lens through which we can view the world around us. Fractal geometry has applications not only in mathematics but also in various fields like physics, biology, finance, and art. It has changed how we understand the complexity and diversity of nature, and Mandelbrot's legacy will continue to influence future generations of scientists and researchers. Fractals, in their simplest form, can be understood as infinitely repeating patterns. Imagine a tree, where each branch is like a miniature version of the whole tree, and each smaller branch mirrors the shape of the larger branches. This repeating pattern at different scales is the essence of a fractal. These fascinating structures challenge traditional Euclidean geometry, which dominated our understanding of smooth, regular shapes. Fractal geometry provides the mathematical tools to describe and analyze the rough, irregular, and seemingly chaotic patterns found in nature and beyond. Euclidean geometry, with its focus on straight lines, circles, and spheres, is insufficient to represent the complexity of natural shapes. These geometries, while useful in many areas, fail to capture the diversity and intricacy of the shapes we see in the natural world. Coastlines, mountains, clouds, and even trees defy simple geometric descriptions. These shapes are not the perfect lines or circles we often see in textbooks. Instead, they have complex curves, irregular angles, and unpredictable patterns. Mandelbrot argued that these natural shapes, often dismissed as rough or chaotic, possess a hidden order, a kind of roughness that can be quantified and analyzed using fractal geometry. He introduced the concept of fractals, a powerful tool for understanding and describing these complex shapes. Fractals are not just a mathematical concept, but a new way of looking at the natural world. He demonstrated that the seemingly irregular shapes found in nature are not random, but follow specific mathematical rules. These rules can be used to predict and better understand natural phenomena. For example, tree branches, river networks, and even clouds follow fractal patterns. This challenged the existing geometric paradigm and opened up new avenues for understanding the complexity of the natural world. Scientists and mathematicians can now use fractal geometry to analyze and predict natural phenomena with greater accuracy. This not only helps us better understand the world around us, but also opens up new possibilities in various fields, from environmental science to technology and art. Part 4. Fractals in Nature. Exploring nature's complexity. Examples of fractals abound in the natural world, from the branching patterns of trees and blood vessels to the jagged edges of coastlines and mountain ranges. Look closely at a snowflake, and you'll discover intricate, self-similar patterns repeating at smaller and smaller scales. The complex patterns of Romanesco broccoli, or the spiral arrangement of seeds in a sunflower, are further testaments to nature's inherent fractal design. These examples highlight the pervasiveness of fractal geometry in shaping the world around us. Part 5. Fractals in Technology. From antennas to image compression. The applications of fractal geometry extend far beyond the realm of pure mathematics and natural phenomena. Fractal principles have found their way into various technological fields, including antenna design, image compression, and computer graphics. For instance, fractal antennas leverage the self-similarity of fractal structures to operate efficiently over a wide range of frequencies. This makes them ideal for use in cell phones and other wireless communication devices. Fractal image compression algorithms exploit the repeating patterns in images to reduce file sizes without significant loss of quality. Part 6. The Mandelbrot set, a universe in a formula. Perhaps the most iconic representation of fractal geometry is the Mandelbrot set, a collection of mathematical points that, when plotted on a complex plane, creates an infinitely complex and mesmerizing image. The Mandelbrot set is not just a beautiful image, but a window into the world of mathematics and fractal geometry. As we zoom into the Mandelbrot set, we find that the detail never ends. Each magnification into the intricate boundaries of the Mandelbrot set reveals new patterns and shapes, demonstrating the infinite complexity inherent in this seemingly simple mathematical formula. Derived from a simple mathematical formula, the Mandelbrot set reveals an astonishing depth of detail upon magnification. This formula, z equals sine z squared plus c, seems simple, but when iterated repeatedly, it produces a complex and infinitely beautiful image. The Mandelbrot set is not just a mathematical tool but a work of art. As we zoom into its details, we see that every small part of the Mandelbrot set contains complex patterns and shapes resembling the whole set itself. Each magnification into the intricate boundaries of the Mandelbrot set reveals new patterns and shapes, demonstrating the infinite complexity inherent in this seemingly simple mathematical formula. This shows that mathematics is not just about numbers and formulas, but a way to explore and understand the world around us. The infinite complexity of the Mandelbrot set is a testament to the boundless beauty and wonder that can arise from mathematical exploration. Each time we zoom into the Mandelbrot set, we discover a new world, with new patterns and shapes never ending. It is a testament to the boundless beauty and wonder that can arise from mathematical exploration. The Mandelbrot set is not just a mathematical tool, but a work of art, a window into the world of fractal geometry, and a testament to the infinite complexity of the universe. Part 7. Mandelbrot's Legacy. A Fractal World. Benoît Mandelbrot's pioneering work on fractals has left an indelible mark on diverse fields, from mathematics and physics to art and computer science. His legacy extends beyond academia, influencing how we perceive and interact with the world around us. Fractal geometry continues to inspire mathematicians, artists, and scientists, driving innovation and pushing the boundaries of human understanding. As we delve deeper into the intricacies of the fractal world, we uncover new insights into the complex and interconnected nature of the universe.